All right, everybody, how you doing today? Good, I hope? Yeah, so I know it's a little jarring to see my name, software engineer, and now I'm talking about hardware requirements, but I do have some experience in hardware field, just, as a kid playing around with computer parts, but also when I first got to PiKNiK, and even to this day, I still do a good amount of system administrative work. So let's jump right into hardware requirements. What will we be going over in this module exactly? Put shortly, Benjamin and Alex earlier this morning did discuss architecture and some of the Lotus components, and then we're going to use that information to dive in a little bit deeper today in this module with some numbers, some examples, and hopefully make things a little bit clearer based on what they talked about. We'll also talk about the consequences of once you actually build your servers with these hardware pieces, and then how to address those as well. Okay, before we get into that though, I do want to say that some of the numbers that we use in some of our systems are based on environmental variables, basically values that you can set, and then those can change the way some processes run, and then also how some hardware pieces are ran. And I'll give an example of that later as well. All right, so first, let's talk about hardware architecture, things you want to consider when you're planning out your servers, what hardware pieces you want. And really, the main thing you want to consider are the responsibilities of what you want the servers to do, basically the Lotus components that Alex was going over earlier. So I went ahead and created a chart here of the 6 main responsibilities. The 3 on the left, PC1 pre-commit 1, PC2 pre-commit 2, and C2 commit 2 are the ones that are in charge of the sealing process, actually getting that sector through the sealing pipeline. Those are normally referred to as your worker nodes. Those are the ones just going through the processes to seal. And then the ones on the right, the Lotus miner node, the Lotus Daemon node, and the Lotus market node are the ones that does your storage provider needs, your deals, and also connecting to the blockchain. So before I get into the numbers on the graph and going over how to read it, I do want to note that these estimates are based on 32 gigabyte sector size. If you are interested in doing 64 gigabyte sector size, I can say that for the most part, you can double the numbers on this chart, but that's not always the case for every single one. So let's go into how to read it. If there is a check mark, that means it is a process that does use that hardware piece intensively. For example, if you take PC1, it requires 64 gigabytes per sector it works on, so there's a check mark there. If there is an X without an explanation afterwards, that means it does not require that piece of equipment at all. So using the same process PC1, you can see that it does not require any GPU usage. If there's an X, but there is an explanation afterwards, that means that while it's not required by the process specific, it's not required by the process, it uses it very non-intensively. So for the PC2, you see that it uses about 15 to 16 gigabytes per sector, which may be a lot if you have dealt with computers before, but if you compare to the 2 next to it, PC1s and C2s, you can see that it is relatively low comparatively. And then lastly, if I put a check mark and an X, that means there's only a moment during the process where that piece of equipment is actually used intensively. Okay, hopefully you've had enough time to look at that. So then some general recommendations when it comes to the hardware that you use. The first thing that we've mentioned many times is that you only want to use enterprise level equipment and you want to avoid consumer grade equipment. Enterprise level equipment are meant to last longer and they're meant to run 24/7, which is usually the case when you're running an enterprise level storage provider. It may seem very appealing at first when you're online looking for your parts, whether it come price, convenience, oh look, there's someone selling on eBay, but I can promise you that cutting corners will end up in a bad result for you. Once the honeymoon phase is over and the piece of equipment is broken, now you're sad and have to go buy another one. Getting a little more specific, I want to mention some scratch space. So the scratch space that you use for sealing on your PC1s and PC2s, for those you typically want to avoid spinning disk. They won't be performant enough for the read intensive and write intensive processes. And then again, consumer drives won't last very long. If you remember Alex's anecdote about his Sabrent that reached over 100% usage in a few months, that's a good example of why you shouldn't use one. CPUs, in general, more CPU cores just equals better performance. It's just a numbers game, but you also want to make sure that you don't over provision your servers because now you're going to have extra resources that you can't use properly. And then also for the CPUs, on the documents, they mention how models with Intel SHA extensions will work better. That's because they do use the SHA checksum within the proof. And then lastly, GPUs, similar to CPUs, more cores equals better performance. And you also want it to be Bell-Person compatible, where a list can be found in the internship documents. Okay, so now we've gone over just the general recommendations. I'm also going to talk about some examples, how PiKNiK does it specifically. Before I get into that, I do want to mention that I'll be using two terms that may seem interchangeable, workers and servers. But I want to differentiate the fact that a worker is just referring to the process, while the server might be more akin to what you think about for like an actual computer, the hardware pieces, the things you plug in, things you rack. All right, so first one is going to be the PC1 server. On this one, the first thing I want to highlight is the 64-core CPU. If you remember me mentioning environmental variables, one of the ones that we do use is called multi-core SDR. What that does is that it enables the CPU to use a whole core complex rather than just a single core to work on a CPU. This will decrease the sealing time. So doing that, it will use 4 cores per sector, and then with a 64-core CPU, we can go up to 16 sectors in parallel, or 15 if you don't want to max out your CPU completely. Off of that is how we derive our RAM and our scratch space. The RAM at 1024, and then use 64 gigs per sector. Calculates to about 15 and 16. And then similarly, if you remember our talk about proof of replication, where the data in a sector is replicated many times to reach about 480 gigabytes, with a 7.6 TIB U2 drive, it also calculates out to about 15 and 16. Next is our PC2 server that will do PC2 work. The core part for this server would be the GPUs. With 3 GPUs, powerful enough to host 2 workers on each one, or 2 worker processes, you can go ahead and fit 6 PC2 workers on this PC2 server. With 6 workers being able to work on 6 sectors in parallel and about 15 to 16 gigabytes per, that comes out to about 90 to 96 gigabytes required for the processes. But 96 is not too friendly when you think about the powers of 2, so we give it 128 gigabytes extra RAM for extra leeway that it has, the server needs to do its calculations. We give it 32-core CPU because the pre-commit 2 process is intense on the CPU throughout the entire thing, and we also go ahead and give it the most amount of scratch space, 3 7.6 TIB U2 drives. And for the last worker server that we have is the C2 server. Similarly, it has 4 GPUs instead of 3, but it also fits 2 workers per GPU, giving us 8 workers on a single server. At 8 workers on a single server and 192 gigabytes used per worker, that equates to about 1,536 gigabytes of RAM. It has a 32-core CPU because it is intensive on that part momentarily, and then it doesn't require any scratch space because at this point, you're not dealing with any sectors that have gone through proof of replication anymore. Okay, so that's the end of the sealing process, or the sealing pipeline workers. Now we're going to go into more of the storage provider nodes. And first, probably most important, is the Lotus miner node. This is the one that's going to be handling your daily audit on window posts. Failing that, you get faulted. Failing that again, you get slashed. This guy's going to be your most important one. Go ahead and give it 256 gigabytes of RAM because at the highest points of window posts, it can reach up to 250 gigabytes of RAM usage. Now, it is very briefly that this amount of RAM is reached. However, being that window post is extremely important, the last thing you would want is for it to randomly crash in the middle of it and then you fail your partition. So we go ahead and allocate it as much as it needs. We give a 16-core CPU because it does have intensive usage at the beginning and end of its proof, just like the C2. And then it also doesn't need any scratch space because it doesn't deal with any sectors long-term. And then it also uses a GPU to do its calculations. I do want to mention that the calculations can be done by the CPU. However, if you decide to go that route, the CPU will generally perform worse and will burn out quicker than the GPU. Next is the Lotus Daemon node. This is the first one that's not required, quote unquote. Technically, none of them are required, but this one can typically be ran on the miner node. However, PiKNiK does host many different miner nodes. So instead of running an individual Lotus Daemon Node on every single server that also hosts the Lotus Miner node, we go ahead and just create an individual server for it that all of them connect to. For this one, we give it 256 gigabytes of RAM, which is definitely over provisioning. But again, like I mentioned, since we have so many miners connected to it, the last thing we want is for it to go down, and now every single one of the miner cannot connect to the blockchain. We give a 16-core CPU just so it can handle the messages it has to send. And then we give it varying scratch space, depending how often we would like to take it down to do maintenance on it. Lastly is the market node. This one can also be ran on the miner node if you would like to provision a single server to do that. But here at PiKNiK, we like to individualize that as well. We give it 1 terabyte of RAM. This is for the sectors that will have to import. When you import a sector, it uses 32 to 64 gigabytes of RAM. And then since we are doing a lot of deals, we would like to parallelize it to make sure they come in and are as smoothly as possible. It has to do some calculations when it imports the deals, so 16-core CPU. And then when it imports the deals, it also stores it on the server momentarily, so we give it 7.6 terabyte U2. Now, I do also want to mention that these are just the examples that PiKNiK uses and how we do it. Obviously, when you guys create your workers or your different nodes, you may find that a PC2 worker and a C2 worker work really well together. You may find a way to combine a PC1 and a C2 worker, and then you create a hyper-efficient server. But at PiKNiK, we like to usually stick with the, I believe it's called the one-to-one bare metal servers. Okay, so we talked about how PiKNiK does it, just the individual servers themselves. Once you go ahead and build your servers, whether like PiKNiK or however you find is most efficient, you'll find that now you have to worry about where you're going to put that and also how you're going to power it. And I feel like these are sometimes not considered because hardware is like more fun and kind of more expensive. So now we can talk about what scales and what doesn't. We'll focus on space and electricity. So first, let's talk about some rack space. Before I get started, I want to mention how you may notice a unit that's just labeled U. If you are familiar with data centers, then you already know that that stands for a rack unit. If not, a rack unit is just the standard unit used in racks at data centers to measure the height of a server. If you like conversions, I think 1U is about 1.75 inches or 4.445 centimeters for European folks. Now that I've gone over that, let's go into this example that I created for why you want to condense your workers. So in this very, very simple scenario, I assumed a data center rack that can handle 45 U's. And then I also took a server that is 4U and then hypothetically fit what we usually put into our C2 servers. So if you recall, a C2 server will have 4 GPUs per server, and they'll have 2 workers per GPU, and then with 11 servers within the rack, that gives you 88 total workers in one rack. After some Googling and a lot of averaging and guessing, I made a random number of 1.2 thousand a month for a single rack at a data center. And then if you went ahead and decided condensing is too much work or it's too much of a headache, you want to separate every single worker, now you have to run out 8 times the amount of racks, putting your cost at about 10K a month. Now, albeit that is an extreme case, you probably won't be doing that. But what you'll more realistically find is that some server cases you find or motherboards that you may find aren't able to support 4 entire GPUs on it. It may only handle 3, maybe 2, but you'll find that even then, your rack space cost could go up 50% to 33%, or however many proportionally to what you take out. And then if you combine the fact, in PiKNiK's case, that we have condensed C2 workers and PC2 workers and PC1 workers, you can see how the rack space can begin to add up. So then with that, you might be wondering why you don't just condense as much as possible into one server, a server that handles 100 PC1 workers and 100 PC2 workers. Well, when you have that many hardware pieces in a single server, if a server happens to crash, there's more factors that it can depend on. You're going to be spending more time wondering, okay, which of these parts is the one that took down my server? And then similarly, if you take it down for a hardware change just for maintenance, it will also take down a larger part of your ceiling power while it is down, whether from a crash or from a hardware change. If you have 80% of your power in a single server, and now you have to go in and change the parts, now you only have 20%. Also, condensing that many parts into a single server also condenses the amount of electricity in use by that server. Problems that would be high heat, you're gonna be playing with fire, uncertainty if a rack at your data center can handle that much power, and also uncertainty if a single power supply can handle that much power as well. And then lastly, you're just gonna see eventual diminishing returns on the pieces that you cram into one server. So after rack space, I also want to mention power. For the power, I want to first give the examples of our PiKNiK servers and the maximum energy consumption used by them. I split them up first into the workers, the PC1 server, PC2 server, and C2 server, and their watt usage at the bottom, their parts, and then also the assumptions I made for their power usage. Now, the important thing to know about workers is that while you're not actively sealing either CC or deals, that these workers can either be idle or even turned off if you are not planning on sealing for a long amount of time. At that point, their power consumption is not much of a concern for you. However, these three nodes, the miner node, Daemon node, and market node, will almost always be running. The miner node and Daemon node, unless getting maintenance performed on them, should always be running, because the miner node will have to be doing its daily audit on your sectors, the window posts, and then the Daemon node has to keep communicating with the blockchain, otherwise you won't be able to do anything. The market node will almost always be running. As storage providers, we would like to import deals as much as possible, as often as possible, but it may have some time off if you are in a lull of deals. Okay, so with that in mind, this is just some general energy tips that we at PiKNiK have used. First is the very simple equation, amps times voltage equals watts. I'm sure if you've ever taken a physics class, then that's an equation that's very familiar for you. So even though it is basic, it is important because that's the one you're going to be using to calculate the amount of watts available to you in a circuit, and the last thing you want to do is trip over that circuit. As an example, let's say you have a 20 amp circuit, and then most data centers will provide you with a 208 roughly volt circuit as well, giving you about 4,160 watts of power. But another thing I want to mention on top of that is that places will often have a fire marshal standard, typically I think set around 80%. So instead you'll have 3,300 something watts of power for usage rather than the maximum amount. However, going over that and you're almost quite literally playing with fire. Next is when calculating the energy usage of your servers, you always want to consider them at their maximum power, even though you may find it rare or infrequent that they all reach maximum power, especially at the same time. Eventually, maybe after a day, a week, a month, a year, they will eventually reach that threshold, and if you don't calculate for that accordingly, then it can trip over the circuit, and now your entire production is going to go down. So with those in mind, it also gives you an important factor to consider with rack location, because you may find that a single rack cannot power many power-hungry servers. For example, if you remember our PC2 servers and C2 servers, both over 1,000 watts each. If you cram all of them into a single rack, it may not be able to support that much. So what you can do is provision it so that it's next to a different server or a different rack that doesn't have as power-hungry servers, and you can power route from one to the other to power your servers. Okay, so now I'm going to go over the chart that you've probably seen a few times now that we've gone over some actual examples of workers, and hopefully you can see the flow a little bit better. So when a deal comes in from the internet, it will communicate with three nodes: the Lotus miner node, the Lotus market node, as well as the Lotus Daemon node. Every single one of those could be on a single server on different ports. After that, it will be imported, processed, and then sent to the sealing pipeline. So for PiKNiK's case, it would just go to our PC1 server, through the PC2 server, and then through the C2 server, back to the Lotus miner where it finalizes, and then is finally sent to the long-term storage. Okay, now everyone's favorite part, the BOM, bill of materials, the BOM, whatever you may know it as, all the prices for the parts that you'll be using or may be using. Now, keep in mind that these prices will be subject to change, just depending on market demand, market shortage, obsolescence, time. But these are the prices that I saw when I was creating these slides. Won't be reading off every single one, but the two that I haven't mentioned would probably be the network interface controller and the storage JBOD. For network interface controller, depending on bandwidth, those could be about 150 to 700. And then the JBOD enclosure could be ranging from 4,000. And then you also have the fail of your hard drives. And that's it.